Okay, so we were talking about inverse functions and logarithms, and we were working this example in the last video, so we're ready to pick up with our next example. I want to solve for x here. The first thing that I'm going to do is get the exponential statement by itself. So e to the 2x plus 3 equals, I'm going to add 7 to the other side. Now I'm going to change this from an exponential to a logarithmic statement. So the power is equal to log base e, so that's ln of 7. Subtract 3 from both sides. I'm going to put the minus 3 in front so it doesn't look like it's inside the logarithm, or so I don't accidentally subtract the 3 from the 7, and then divide by 2 to get x by itself. So we'd have negative 3 plus ln of 7 all divided by 2. Our change of base formula. Again, we learned this in college algebra. Log base b of x we can rewrite as log base anything of x divided by log base anything of b. So ln is a perfectly fine choice. Since it can be log base anything, why not be log base e? So I would use this to evaluate something like log base 8 of 5 correct to 6 decimal places. What I would do there is I would rewrite that as the natural log of 5 divided by the natural log of 8. Plug that into my calculator. You're going to get about 0.774. All right, we want to sketch the graph of the function ln of x minus 2 minus 1. So we're just going to start with the graph of ln of x, which we know looks like this. Now the minus 2, this is a subtraction inside the function. So for our transformation section, we know that moves me right 2 units. So I'm just going to move the whole thing right 2 units, including that vertical asymptote. And then the minus 1 is outside the function. We learned that moves us down. So instead of passing through the 0.30, we're now going to pass through the 0.3, negative 1. Now remember that the domain over here on the original graph was 0 to infinity. So if I move it right 2, my domain is now 2 to infinity. Okay, does that make sense? All I did is shift everything right 2 units. Now the down 1 doesn't affect the domain. It could affect the range, except remember my range here is all real numbers. So if I move it down 1, it's still all real numbers. Those were our logarithms. Now we're ready to talk about inverse trigonometric functions. Excuse me. Okay. So if we're going backwards from our trig functions with the inverse trig functions, instead of saying, here's the angle, tell me what the sine of it is, we're doing the reverse. We're saying the sine of something is whatever, tell me what the angle was. Now, in order to have an inverse, we know we have to be dealing with a one-to-one function. Sine and cosine are not one-to-one. If we pass a horizontal line across that graph, we see we intersect in a lot more than one places. So we have to restrict to a segment that is one-to-one. For the sine, remember, we restricted from negative pi over 2 to pi over 2. So then the bottom value here is a negative 1, and the top value here is a positive 1. So we're restricting the domain of the sine to go from negative pi over 2 to pi over 2, the range negative 1 to 1, in order to create the inverse. So my inverse is created with the same definition that we used before. Inverse sine of x equals y is equivalent to saying sine of y is equal to x. The y is restricted to be between negative pi over 2 and pi over 2. On my unit circle, negative pi over 2 is down here, and pi over 2 is up here. So I'm going only in the first and fourth quadrant. Okay, so we're asking to evaluate inverse sine of a half. We would be looking on our unit circle and saying, where does the sine value, which we know is the y-coordinate, have a value of 1/2? Okay, so we know that happens at pi over 6. So inverse sine of a half would be pi over 6. Now, if I want the tangent of the arcsine of 1/3, this value right here is not on the unit circle. So instead of using the unit circle, I'm going to use a triangle. So sine is my opposite over hypotenuse. So the statement sine of theta equals 1/3 allows me to label this side and this side on the triangle. I now use my Pythagorean theorem to find the remaining side. Then the tangent of that angle would be my opposite over the adjacent. So this value right here. This is our composition property. This is what our graphs would look like. Notice that the domain and range flip places. So inverse sine is going between -1 and +1, the range from -π/2 to π/2. We make a similar restriction for cosine, but this time it's 0 to pi, so first or second quadrant of the unit circle, instead of the -π/2 to π/2 that we had for the sine. Same composition properties. Give me back just x. Here is the graph of the inverse cosine. Again, it's the domain is -1 to 1. The range is 0 to pi. It means the same thing as with the sine. We're getting back an angle that generates whatever that value is for the cosine. Inverse tangent goes from -π/2 to π/2. So we've had to restrict the domain of the tangent in order to make it 1 to 1. So when we look at the graph of the inverse tangent, which we get by reflecting across the line y equals x, right? So if I just dash in y equals x there, we're going to see that we're going to have a horizontal asymptote at -π/2 and at +π/2. And my inverse tan is going to look something like that, okay? So you need to be able to work with all of these functions, know the domains and the ranges and the properties that go with them. Here are the remaining 3 inverse trig functions. You do not have to have these memorized, but you need to be aware that they're there and you can use them. But we're going to be sticking primarily to sine, cosine, and tangent.